Everyone. Today we're going to present that previous topic. I think last week we could not present that properly. So due to my issues, my laptop power shutdown. Okay. So once again, I repeat that somewhat important things. So did you see that PPT right? Yes. Yes or no? It is visible,
Yes,
right?
sir.
Okay,
Yes,
fine.
sir. Visible.
Okay, fine. So some classifications of the basic electronics. Okay. So before they enter that detail about that electronics, we need some basic things. I think you're studying that physics itself in lower class, maybe 11th or 12th, and college also you study that physics papers, right? Physics 1 and physics 2. Somebody is you're studying that those things. Okay. So here just given some basic things only. Okay. So just recall about that what are the classification before what you are studying, that only to classify that everything. So here classification based on that conductivity. Okay, that is conductivity is nothing is the flow of electrons in the line. Okay, so based on the cases only we have to justifications of that different types, different elements. Okay, so here conductivity as well as resistivity and some energy band also. Okay, so basically there is three types for the solid classifications. One is a conductor, another is a semiconductor, and third one is the insulator. Okay, we can call the other name metal also. The metal is nothing else, so the conductor only. So that is it. Normally, conductor is a very good conductor on the conductivity. Very good will be good condition for the flow of electrons, and the semiconductor also partially conductivity. Okay, so not fully that fulfilled conductor. It's like a partially conductivity. And third one is the insulator, that is a bad conductor. We can't passes through the line, the power flow of electron we can't passes, right? So that is a small examples when I put that some video previous class, I think so. So like a stadium. Okay, so when a stadium representing that open the door, the people are enter that different, I mean the whole batches will be enter the single gate. Okay, so there is all the persons will be enter. Okay, the all the electrons should be enter. There is a good conductor. Okay, so there is no disturbance in the anything else. But in semiconductor it enter the gate, but it will be one by one persons, like, right? The electron should be like a flow of conductivity will be the one by one condition will be process in the line. Okay, so that is called semiconductor device, right? So the electron should be the flow will be continuity, but the enter the electron in the gate will be single only. Okay, not in the group format of the electron should be formation in the metal or conductor. Okay, so but in case of insulator, the three gate is that the group of the peoples not enter. That will be we can't to enter the gate. Okay, just the once it passes that leave it. Okay, there is no passing through the particular line. What happened? Who's this? Praveen Prabha, please mute your mic. Yes. Okay. So insulator normally there is no flow electrons will be inside that. That is a very bad conductor. Okay. So that is it. Basic things when I classified for the solid conditions. So one is a metal, semiconductor, insulator. Metal we can call the other name. What is it? Conductor also. Okay. So next band, we discussed last class also some three figures we are defined for the conductor as well as the semiconductor and the insulator. For the energy band also we define that. So what is the energy band? I think the solid material, the electron energy level from band of the allowed some energies. Okay, some separated by forbidden gap. Okay, that is a forbidden band. Okay, So between the which that energy will be separated means that is a either valence band between the conduction band. Okay, so this two band will be between the some gap, energy gap will be available. So what is by valence band? So valence band is nothing else, that is the outermost band. Okay, that is the highest band, we can call the other name, we can call the highest band also. It's filled with some electrons. Okay, so filled with the electron means the field is equal to all state occupied. Okay, so normally the states are all occupied the conditions, that is called the valence band. For conduction band is nothing else, that outmost band, so higher than that conditions, that is the next highest band is equal to the valence band. Okay, the valence band is above the regions be some conduction band. Here the field, okay, the normally that electrons will be filled will be either empty or partially filled. Okay, there is not full occupied the all the state, so only that few condition only as it is possible. Okay, already I said that what is the gap, the gap is nothing else, energy difference between the valence and the conduction band, that will be equal to, we can call the width of the forbidden band, or else we can call the width of the forbidden gap also. Okay, so this is a energy band we can call. Okay, so next next, that's the figure. Okay, we can see that some nucleus that atoms is the positive ions, and some shell, different shell is there. So first band, second band, third shell will be valence band, and above that valence band will be a conduction band. Okay, so between the conduction band and valence band some gap is there, so that gap is called forbidden gap. So this is it called forbidden gap. So here when you're discussing that the electrons and holes, so when you discuss that electrons is a completely filled band cannot move. Okay, that is normally cannot move since all state will be occupied, is like a Pauli principle. So only way to move would be jump. Okay, it should be jump into the next higher band, that is called the energy. Okay, need some energy. So when you jump over to the another band, so normally the electron is a partially filled band can move since that there are free states to the move to the another state. Okay, so that is called the some important points when you know about that free electron should be how you move. So there is a electron when you called two way. One is the free electrons, another one is that bond electrons. When you're saying that free electrons, so free electrons normally that will be, we can move that freely for the one side to the another sides, or one state to the another state. Okay, so here there is no without Coulomb attractions forces for the nucleus, for this free of electrons will be there. So normally the electrons without a Coulombian attraction force of the nucleus. For example, when you're saying that bond electrons, so the electron should that moves around the nucleus. Okay, around the nucleus, the nucleus only have to some bond electrons should be there. So this electrons, the normally feeling that feel there is a Coulomb attraction will be appear forced with the nucleus condition. Okay, so that is the main difference between that. One is a free and another is a bond. Whenever saying that free electron that will be moves the freely one state to the another state, but in case of bond electron that not moves only the around the nucleus. Okay, should be moves in the nucleus only. So here there is no Colombian attraction force of the nucleus for the free electron in the free electron. But in case of bond electron, some electrons should be feeling the Colombian attraction force with the nucleus. Okay, so when you're saying that there is a electron as well as holes. Okay, so normally the atoms will be present. The two things, one is the electron, another is that holes will be there. That any type of conductor. For example, say either conductor, or else you can say that semiconductor, or else what is it, insulator. Okay, it will be two will be present. One is the electron, another is the holes. So here holes will be created by means that by electron only. Okay, so normally the uh, bond will be damaged, I mean broken. Okay, so once the bond will be broken, so automatically that create by some holes. Okay, so that I mean it should be vacant. Okay, that electron should be vacant. So that vacant only it's called free holes. Okay, so that will be holes. So it is a vacancy created by electrons only. That is called the holes. So small examples. So I will be created by the holes. So see that there is a energy level with the electron pass. Okay. So normally the positive negative ions will be there. So bond to the conduction band. So that is a freely moves that. So once moves that, so they will be creating some vacancy. Okay, so this vacancy is called the holes. Okay, so when you compare the free electron as well as holes, it be equal to electron hole pair. Okay, so I will be create that those things means used on the energy. Okay, so some energy given to the particular material. So based on the energy only you have to create the holes. Okay, should be yes, space will be appear and create by some holes, right? So these are the four electrons. So that is four atoms will be there. Okay, around that ions, the four ions will be appear. So once the energy will be created, so automatically the electrons should be moves towards the one side. So once the moves to one side, they create by some holes. Okay, so this is a small basic structure. When you seeing that both energy diagram as well as the bonding diagram. So how will be bonding to the each other. Usually there is a four valence electron valence band. Okay, so around the particles, so that will be collide to each other. Okay, that is normally the valence electrons will be collide to each other. So some energy is given to the particular this electrons means. So automatically what happened, that will be some created by some holes. Okay, so this is called how will be energy diagram create as well as bonding diagram will be create. Okay, so when you saying that current, okay, so usually the passes through the in conduction band. Okay, so how will be current flow through the that line means or else that device means is a small examples. Normally when you use that either silicon or as germanium. Okay, that is the element element we are using for that, either silicon or else what that particles, that is a germanium. Okay, so inside of the germanium silicon, so around these some four valence band. Okay, so four valence band is there. So with combined the two silicon, that will be collide to each other. Okay, so normally collide to each other. So once this bond will be broken, okay, so this bond will be broken here as holes will be created. Okay, so this once holes will be created, automatically this electron should be moves to the this vacancy holes will fix that. I mean it will be goes to the particular um, vacancy positions. Okay, once this electrons goes to the this vacancy position, then now we create by this here also some holes. Okay, so automatically I have what happened. So nearby what the electron will be there, that electrons moves to the that vacancy positions. Okay, so this is normally doing for that around the holes created as well as it moving the electron also. Okay, so this is happened the conduction band. So whenever the supply is given, how will be energy is given to the particular uh, the diodes or either any kind of material means, what will give that directly, I mean supply is given to the particular medium, right? So when supply voltage is applied to across the piece of the this is a two types of types is available for the semiconductor device. So one is the intrinsic semiconductor, another one is the eccentric semiconductor. Okay, so this type of that path is called intrinsic semiconductor, the silicon, intrinsic silicon. So the thermally generated free electrons in the conduction band are now easily attract towards the positive end. Okay, so this movement of the free electron, one type of the current in the semiconductor material, and is called the electron current. Okay, electron current. Okay, so I will be create. Okay, that is at this structure. So I elaborated the whole structure. So how the electrons will be free. So normally the silicon material is there. Okay, Si is a silicon material. So around the some what is it, either a pentavalent or trivalent valence band will be around the silicons. Okay, so here how many electrons will be there. So 1 2 3 4 valence electrons is there. Similarly, another silicon, one more silicon also, the 4 valence band is there. So once that the band will be collide to be each other. Okay, so either two atom, two electrons to be each other. So here the different state is will be created. Okay, so first initially the free electrons leaves holes in the valence shell. Okay, so once the energy level is given, so automatically this electrons will be moves to the one positions to the another positions. This electrons will be, it comes to here. Okay, so then again the first holes leaves and second holes will be create, and similarly second holes will be leaves and third holes will be create. Okay, and similarly third holes will be leaves and fourth hole will be create, and similarly fourth hole will be leaves and fifth holes will be create. Okay, so like that way that the valence electrons moves to the one to the another each other. Okay, so this is that valence electron will be effectively moves from right to left or left to right. Okay, so just occupy the cells. Okay, so occupy the cells for the free electrons. Okay, so this is the one condition. How will be the electrons, the electron free will be appear. Okay, the different structure when you are representing that. So 6 protons, so that is at valence electrons will be 4 around the particles. That is a 1 2 3 or 4. Okay, so the outermost region is nothing else called as a valence electrons. Here the 4, and this one also the 4, and here also that a different one valence electron. Okay, so depends upon the structure as well as we are designing the process. It should be varying that valence electron as well as the core region also. Okay, so the core region here the +4, here also +4, here the only the +1 will be appears. Okay, the energy diagram. So in energy diagram, based on the material, we can differentiate that each energy level will be should be variations. Okay, so for insulator there is an energy gap will be should be high. There is some energy level will be more than conditions, that is at between the valence band as well as conduction band. So the energy gap will be high. So in case of semiconductor, somewhat energy level is up here, so between the conduction band as well as valence band. But in case of conductor, there is a good conductivity. There is no energy band is available in the conduction and conduction band as well as valence band. So there will be some overlap. Okay, so that overlap is that marked as a pink color. Okay, so this is the overlap condition only as it is possible. Yeah, that should be explanations given. So when is that so when metal. Okay, so you have to metal, how will be the metals electrons should be moved to the one positions mean used on the energy level. So based on the energy level, you have to representing that some equations. So here that some examples I taken from that some books, that is that solid state electronic device 6th edition by Benji, okay, and Sanjay Kumar Banerjee. Okay, so based on that books will be taken some reference for that. I will represent the equations. Okay, so normally there is a two pictures show it here. So A and B. So A is nothing else, the electrons will be ejected from the surface of the metal when exposed to the high to light frequency in the vacuum. Okay, so normally the vacuums, light vacuums passes through the this metal, so automatically some expose the some surface, so the electrons to away. Okay, so this is the electrons. Okay, this is the metal. Okay, the light normally what is that equation we can representing that. So E is equal to H. H is at the Planck constant. Okay, I think you're studying that physics, that is a Planck constant, and V is at some velocity. Okay, so we both will be represented as a H and V as equal to light. Okay, that is the energy level. E is equal to H into V. I think you studied this physics itself. Okay, the same thing equation will be representing here also. So based on the equations, you have to plot the maximum kinetic energy of the exiting electrons with the frequency. Okay, so this is a maximum energy level, that is a kinetic energy level. So EM we can represent that, and that is a y-axis. When a x-axis is representing as a that frequency of the incoming light. Okay, so the light will be incoming the conditions. So based on these two values, you have to express that graphically representing that. So this nothing else as a slope, it will becomes like a slope format. Okay, how will be that plotting that between the maximum kinetic energy as well as that frequency of the incoming light. It be like it goes to the energy as well as velocity of the light, means it be goes by like a slope. Okay, it should be slanting positions. Okay, so the slope is equal to h, that is a Planck constant. Okay, that only you have to represent here. The equation will be representing E is equal to hv. So that slope is called h Planck constant. Okay, we are representing as a h, define that. Okay, so next the same thing. Okay, the energy between the one energy to the another energy. So normally how will be that the energy passes through the Planck constant with the representing with the frequency of the domain. Okay, so that will be equal to energy level. E is equal to hv, the same equations. Okay, so based on the energy equations, we can represent the some specific nature, that is a specific some crystal range. So normally this and all you study in that physics itself. Okay, just recall that topic only. Okay, but we're going to entirely discuss that main things is what is a semiconductor. Okay, so the semiconductor device only to discuss for the intrinsic and the eccentric semiconductor. So previously when you're going to discuss that I mean, detailing before that, knowing that what is the basic things. Okay, that what I put that here, the specific of the crystals. So between the conduction band as well as valence band for the energy level. This is the energy level of the conduction band. Between the some forbidden gap is between the two conditions. So that will be normal. Both will be equal condition. That the equal condition is a some Fermi level. Okay, that is the energy Fermi level will appear. So that level is called Fermi level. Okay, so normally this is atoms. Okay, so when atoms the electron orbit in the cell at given some energy. Okay, so in maybe the crystal, so may electrons occupy small energy band. There is a width of the energy width to the energy band. So which is already we discussed that the Pauli principle. This the same. So here the Pauli explosion is not violated. Only in the within the principle only is possible in the crystal. So within the band, the electrons can move easily if there are available states, because the different the energy is denied. So between that what is it between the band, between that band as well as they compare that source another source some this, because that band gap will be significant natures. Okay, so there's a basic things. um, we go for detailedly discuss the semiconductor material. So that is a special class of the elements having the conductivity between that the good conductor. This is also good conductor only, but some partially filled that electrons. Okay, so and that of insulator. Okay, so there fall into two classes. So a single crystal as well as compound. Okay, so single crystals examples we can say that germanium and silicon, that is called a single crystal. So compound means that is a gallium arsenate and gadolinium sulfate. Okay, sulfate nitrate and gallium arsenate phosphate. Okay, so those things we have discussed that for the compound, and only that single crystal for that means the silicon or either germanium. That material only we are classified in the two sections. Okay, so when you're going to knowing about that when you will happen means as the historical conditions. So initially, the developed that based on the germanium, developed by 1939. So used to develop by the diode, and 1947 using the germanium transistor they developed. So 1954 only they used for the silicon. Silicon was used in the transistor because silicon is a less temperature sensitive, so abundantly available. Okay, so when you saying that high speed transistor was using by gallium arsenide in 1970s, so which is a 5 times the faster compared to the silicon. Okay, so why go for that gallium arsenide means that because of the speed of the transistor only we go for the 1971 because that 55 times faster. Okay, so compared to the silicon. Okay, the silicon, germanium, gallium arsenide so are the semiconductor of the choice. Okay, so mostly the silicon is that used to that our country as well as Germany also. Okay, so compared to the other material, so mostly probably they using the silicon only. Okay, these are the different chart. I think your chemistry you're studying that how that the gallium atoms are present that band atoms will be available. Okay, the gallium, germanium, arsenium, and silicon. All the materials available in the chart. Okay, I think you're studying the chemistry properties. Okay, so directly go for the some structure. So this is a basic structure: 32 orbiting element electrons and 14 orbiting electrons. This is a tetravalent, and this is also some tetravalent using the conditions. So silicon, that is at the center of the positions, you know that it's a nucleus. Okay, so around the some cell is there. So valence cell is our last entered positions. That is a 4 valence electrons. 1, 2, 3, 4 is available. So between the do some orbiting electrons will be inside that conditions. Okay, this is a germanium. The germanium is at nothing else. Just orbiting electrons will be 32. So others will be the combined that valence electrons outer region will be the 4 only. The remaining electrons will be inside that. The orbiting electron will be inside that structure. Okay, this is a small basic structure only. So I skip that. No need to discuss more than that because that you already discussing in physics itself. Okay, so there's this basic structure covalent band, the covalent bonding of the some silicon crystal. I think this video I will show in the last conditions. So how will be that back or valence band as well as covalent band will be creating that some video picture is there. Okay, that will be I show it. Okay, that you know how will be create that a covalent band as well as valence band then create by the holes. Then I will be fixing that the holes will be holes will be created by electrons will be created by holes, and I will be goes to the electron goes to the that particular holes. So everything will be discussed in the that we show it in the video. Okay, so here each and every isolated electrons a specific energy level so associated with the cell and orbiting electrons. The further an electron from the nucleus, so here is the energy state. The electrons left its parent atom as high energy system. Okay, size within that any electrons in the atomic structure. Okay, so these are the analysis part from the chemistry part. So the same thing whatever that they before they saying that the same thing will be saying that. So I will be free state conditions already said that what is it free state. Okay, so I skip that and all. So some intrinsic carriers as a semiconductor. So how much intrinsic carriers will be appear the gallium arsenate 1.7 into 10 power 6, and silicon will be 1.5 into 10 power 6, and germanium will be 2.5 into 10 power 6. Then relative mobility. Okay, the relative mobility of the different material. So here the relative mobility of is the mobility of the free carriers to move through material. So here the semiconductor based on the relative material will be 1500 for silicon, this germanium for 3900, gallium arsenate will be 8500. Okay, So then the effect on the temperature, based on the different material. So normally the conductor increase the resistance with the increase in heat. Okay, so it's said to be positive temperature coefficient. Okay, so here the number of carriers do not increase. Okay, so the carriers do not increase, so only that increase that resistance with the increase in the heat condition only. Okay, so it should be said be that positive temperature coefficient. Okay, for in case of that semiconductor, so increase the conductivity with the increase in heat, it's said to be have a negative temperature coefficient. Okay, so here previously only the number of carrier does not increase, but here the number of carriers also here increase. Okay, so that is the difference between the conductor as well as semiconductor. Fermi energy level, so already they said that the Fermi energy level between the covalent band, valence band as well as conduction band. So here some definition we can call that oil B energy level, Fermi level be create means the highest energy on electron reached by your field the solid with the intrinsic number of electron at absolute zero. Okay, there is no added thermal energy. Okay, only that using the highest energy level reached if you are to fill the solid with the intrinsic number of electron at absolute zero. Okay, so meaningful, this is there is some sea of electrons sitting the beneath of this energy. Okay, if you bring two solid together with the different Fermi energies, the electron will move around to reach equilibrium. Okay, the foreshadowing the BN junction. Okay, so when you're discussing the BN junction, so that time we will discuss that Fermi energy level also. So I'll be create that. Okay, so with the some video also representing for that how will the energy will be creating that. So this is a small examples the combinations of some n type of semiconductor. Okay, based on the extrinsic semiconductor, there is a two type of semiconductors available. One is a p type semiconductor and is a n type semiconductor. So what is it? P type n type means that is the valence electron and conduction band. Okay, so based on that electrons or holes are created. Okay, so that will be occupied filled by the electrons that in holes. Okay, so that will be changeable, type will be, formation will be changeable. Okay, so based on that formation we have to differentiate either n type or p type. Okay, so that also we discuss that detailing. Okay, so here the based on the Fermi energy level, you can represent the equations as the level of the single quantum number n and energy is given. Okay, so normally energy, you know that formula general, I think you studied this. Now see the PPT. Anyone answer? Maybe yes. Did you see that PPT? Yes or no? Yes. Okay. Okay. I think this is a study in your physics itself. The same. I can recall that the equations. The level of the single quantum number n and energies are given as En h square pi square divided by 2m l square n square. What is the h? Already I said that blank constant. So n is nothing else quantum number, and m you know that mass number. L is always in the length of the side. Okay, so these are these simple equations. I think you study in the physics itself. Same thing. I recall these equations. So easy, nothing else. That based on the blank constant, some constant values, the pi square divided by the mass of the element with the length of the sides of the electrons, as well as that quantum numbers, and the number of quantums will be available in the atoms. Okay, so these are the energy level which equation be representing that. So when you go for the Fermi energy level, so maybe differentiate that quantum number will be changeable. Okay, so normally that Fermi energy level, the number of particles divided by half of the positions. Okay, already that conduction band, valence band, so within the half positions only. Okay, so when it's half the positions, the number quantum number also divided, so we can represent the here particles n by 2, that whole square. Okay, the spin is half, so that what we are representing n by 2 whole square. Why means because there should be half positions only. We are fixing the between the conduction band as well as valence band. Okay, so that is called Fermi energy equation. For the when you going for the dimensions, okay, so normally you're structure oriented, either 2 dimension or 3 dimensions. When you're going to discuss that Fermi level in the 3 dimensions, so equation representing as a vector format. As vector format, when you see when you put that vector format, always that some this like a two bracket. Okay, it's a back simples. This simple within the arrow mark indications. This is the arrow mark indication as a vector format. Okay, so this is a magnitude indication. This is a magnitude indications. Okay, so double quote we have put that means column will be put that means that is nothing else. Yes, what magnitude? Okay, should be either negative also, it will be in a positive only. So that is the meaning of that. Okay, so that is the same equation I am representing. So only I removal of that what is it vector format I put. Okay, so the arrow mark will be indicate means that is a vector. Okay, so the number of fermion is given. How to find out the Fermi means already you know that n divided by 2 whole square. Okay, so based on the n by 2 whole square, so n square by 4. Okay, so n square by 4 means that is the n 4 into 2 8. Okay, so everything reversible means we getting the sum the equation like that 2 into 1 by 8 4 by 3 pi into n cube into f's. Okay, so this is the Fermi level. For that, when you're going to find out that the NF means, therefore, when equation should be like 3n, the pi, the root of 1 by 3. Okay, so just a reversible of this equation. Okay, so rearrange the equations. Okay, so once 1 minute. Okay, so once we rearrange this equation, maybe we get that NF is equal to 3n by pi, the power of 1 by 3. Okay, so just put instead of this reversible, right? So we get that value of NF. Okay, then Fermi energy level is, you know, that formula, previously formula, you know that. So the same thing that you put it that instead of NF, we can replace that. Okay, we're getting the somewhat expression that is that EF is equal to s square by some 3 1 minute. Start that. You get the PPT? No, right?
Yes, sir. Yes, sir. We got a PPT.
Oh, okay, okay, fine. One minute. Maybe stuck for me. Okay, so equation B as replacing L square with the V square by V root of 2 3. Okay, using that conditions, maybe V is nothing is volume. Okay, so by length square we can replacing the volume. Okay, so we will know that length will be changed the volume means we are studying the mathematical itself. Okay, so used to for this some root of 3 conditions. Okay, so once you use that, that is a cubic. Okay, so normally the cubic format when you change that means so volume will be representing, right? The same thing here also the energy level change to the volume conditions. Okay, so used to for the 2 power of 3. Okay, so the power of 3 will be as used that. Okay, so when a typical energy level of the nucleus, so R will be representing as a some equation be like 1.25 into 10 power minus 15 m, and these are the common value. Okay, so using that for that A is that nothing else nucleon between the protons and neutrons. Okay, the power of 1 by 3. So the number of density of the nucleon in nucleus is that n, that is a small n is nothing else the number of density of the nucleon in the nucleus. So used in these conditions maybe getting that A divided by 4 by 3 pi through r power 3. Okay, so approximately getting that number of density of the electron in the nucleus is at 1.2 into 10 power of 44 micro per meter cube. Okay, so the per meter cube, we have to replace the per meter cube means the m power of -3. Okay, so the permanent energy of the nucleus conditions, so rewrite that all the equations. So what are the getting the variables, we are substituting that. So finally we getting that approximate values. So instead of n, you have to replace 1.2 into 10 power 4, the previous equation. This equation you have to substituting that values. So we getting the sum out expression will be like 30 into 10 power 6 electrons volt. Okay, so this is the 30 megavolt electrons. Okay, this is the expression for the energy level of the some Fermi energy of the nucleus condition, that is a EF is equal to, so overall we getting that value of 30 volt electron volt. Okay, so this is a Fermi diagrammatical representing that. So how will that statistics, I think there's not all no need that. Okay, you directly I go for that different solid condition, because that based on these solid conditions we have to differentiate different three device, that is the three material. One is the insulator, semiconductor, conductor, already discussed. Okay, so only that representing of the energy level only here representing. So always the energy level here the greater than somewhat 3 electron volt. Okay, so the energy level will be high compared to the other conditions. For the when your semiconductor electrons will be it's like 0.61 electron volt for germanium. So eg for the energy level for that Fermi level for that what is it silicon means 1.1 electron volt. For that gallium arsenide means 1.43 electron volt. But in case of the insulator, there is a more conditions for the energy level, because that there is no I mean the conductivity. Okay, there is no conductivity, so for that energy level will be high, so that is unable to reach the conduction level. Okay, that will be more. But in case of that conductor, there is no energy level, because there is some overlap between the conduction band as well as valence band. Okay, there is no conduction, I mean energy gap. Okay, there is no Fermi energy level also. Okay, should be free condition. But we going to discuss the semiconductor only. So you know about those things only. Okay, so which are that germanium, silicon, gallium arsenide, these are the important things knows that when you going to some discussing the problems and all, used that energy level value of that either is germanium or silicon gallium arsenide means used to this value. Okay, 0.67 electron volt and 1.1 electron volt and 1.43 electron volt. Okay, so these are the values for the different state condition. So based on these values we can find out the conductivity relative medium, that with the respect to resistivity and conductivity. You know that conductivity simples, that is sigma. When using the conductivity simples is a sigma. So I will be representing the resistivity means the reciprocal of the conductivity is called a resistivity. Okay, so that is rho is equal to 1 by sigma. Okay, so based on this expression only you have to find out the different materials range of the values. Okay, so in metal there are the solids which have a low resistivity or a high conductivity. So hence sigma will be sigma representing with the value. Okay, depends between the 10 power 2 between 10 power 8. Okay, so this is the value between that condition. So the sigma rho will be 10 power minus 2 10 power minus 8. Why negative becomes means that is the reversible of the conductivity. What are the values will be getting, same thing you put in the reverse manners. This is resistivity normally used the ohms, and conductivity will be sigma is used that is per meter. Okay, so insulator the same thing you have to find out that. So here there is some high resistivity or low conductivity. So hence that equations representing the sigma, the 10 power minus 11 and 10 power minus 19 for the sigma. But in the case of the resistivity, the same thing, the plus condition will be appear. When you go for that semiconductor, the solid state will be high restrictive, have high restrictive, as well as connective values between those metals and insulator is given. So sigma 10 power 5 between the 10 power minus 6. Similarly, rho will be 10 power minus 5 between 10 power sigma 6 ohms. Okay, so that is the basics classifications of the material. So this is the classification first topic. Okay, so there is a classification of different material. So how will be energy level will be formed. Okay, so what are the element valence band as well as conduction bands available, and all the energy level will be created, and what are the metals, I mean based on the metals, what is the range we are using for that connectivity. Okay, so these are the discussing today. Okay, so one peep, I think it won't come. I stop that. Maybe the end of sections. So I told one video and conclude for that one. Already this one I shared before. Video not running. Okay, 1 minute. Okay, now visible, right? Yes.
Yes,
Yes,
sir.
sir.
I think this videos already put that, right? So maybe some the electrons, right? So example cricket stadium, when I say that, right? Yes or no? Yes, right?
Yes, sir.
Yeah, the electrons how will be insulated? The gate will be closed. Okay, there we can't enter that electrons. Okay, so that is called the insulator. There is no possible to the flow of electron will be available in that insulator. The same thing. Okay, initially that Alexandra Volto 1782 itself finding the designing the device, the semiconductor device. but the laterally they decide for the 1833 Michael Faraday based on the silver sulfate, using that silver sulfate, use the material, you have to find, they have find out in the semiconductor device. And you know that already, this and all I discuss. Okay, intrinsic semiconductor, there is two types. One is the intrinsic semiconductor and this is the eccentric semiconductor. When you're saying that examples of the intrinsic semiconductor and as well as the silicon and germanium, okay, this is also we discuss. Okay, how will be the electrons? Normally that the valence electrons, that is a blue color indication is a valence electrons. That's for the normally the 4 electrons will be there. So when you combine two things, the 2 silicons will be combined, we're getting that 8 electrons. Okay, so maybe that between the, this is nothing else, the main concentrations. Okay, so clearly see that how the electrons and holes creating between the silicon material. Okay, so I will be created by the holes. Okay, and I will be occupied the holes and electron also. Okay, so normally this central positions, okay, the 2 electrons the combine, one silicon another silicon combined to either together, so it may becomes 8 electrons. Okay, so that is called a bond. Okay, so once the bond will be creating that, so that bond is nothing else covalent bond. Okay, so the between the 2 point. So once they increase the temperature, okay, so normally increase the temperature, automatically the bond will be broken. Okay, so once the broken that bond, okay, so the electrons will be create that particular place as a holes. Now create by that fix that nearby electrons will be uh, electrons moves to the that particular holes. So similarly that is created by other region also, same like that will be happen. Okay, around the all the silicon material. Okay, once create as well as combine the covalent and similarly create and combine. Okay, so this may be happen. Okay, that the energy level will be inside passes through that. Okay, so this is that intrinsic and extrinsic semiconductor. When you saying that intrinsic semiconductor, when you go for that extrinsic semiconductor, what is the difference of that condition means? Only thing, this is a pure form. Okay, when you're saying that intrinsic will be pure form of the semiconductor, but extrinsic semiconductor you have to add some impurities. Okay, for the improving of the conductivity, that is improve conductivity we have to add it. So one is that extrinsic semiconductor, there is a two types. One is a B type and is a N type. So P type is called trivalent, the 3 valence electrons around that particles, the orbit. Okay, so when you are around that orbit, it will be 3 valence electron. But in case of N type, so 5 uh, 5 valence electrons. Okay, so that is a pentavalent. Okay, so normally example when you say that boron as well as that one is a. Okay, so one more thing, so that you consider that, so the silicon, so I will be gone covalent band energies boron as well as added. Okay, so once I think this is the extrinsic semiconductor, previous one is a intrinsic semiconductor. Here see that will be energy impurity will be added. Okay, so when you add the boron, so the electrons moves to the collide to each other, the same thing will be happen. Okay, so collide one electrons moves to the another things means another phase means automatically they create by holes. Okay, the red mark will be there, right? So they then again the electrons will be nearby, electrons will be goes to the particular poles. Okay, similar way they will be happen so all such things. Okay, so this is a small examples when you using the adding the some impurity of the material. Okay, so this is called the extrinsic semiconductor. Okay, this is a boron or else either phosphorus. When you're saying that, when you're saying that P type you used for the boron, for even going for that N type type of semiconductor used for the phosphorus. Okay, so the N type normally that 5 valent uh, 5 valence electrons should be available, that is called the pentavalent. Okay, the same thing they around the each other. Okay, they see that the same structure. Okay, the same structure, the phosphorus inside the that particular silicon purity will be added.
So once eliminated, they create by some the covalent band. Okay, so some extra flowing electron is possible in case of phosphorus, because we are using for the pentavalent, right? So that extra electrons will be moves towards around the that phosphorus. Okay, so this either anyway we have to go there. Okay, but initially what is that intensity conductor, the same thing will be happen. Okay, so just a review of that semiconductor review that. So what is the material already that saying that what are the material conductor, copper, the pure conductor, that is a conductor will be good conductor will be copper. Then material for the insulator, either wood, mica or paper when you're using for that insulator. Semiconductor either using germanium, silicon, anything. Then semiconductor, what are the semiconductor, you know that intrinsic semiconductor and eccentric semiconductors. And intrinsic semiconductor, the purest form of the semiconductor. Okay, so there is a structure based on the silicon material used to be two conditions we all discussed. When you extrinsic semiconductor, what is it, impurities will be added, either boron or phosphorus. Okay, so once you added that, how will be that nature will be formed. Okay, that the structure you see that in a ppt, I mean videos. Okay, so here there is extrinsic semiconductor, there is a two types, one is a p type as well as n type, the boron and phosphorus. Okay, that's it. Structure also is put that. Yes, are clear now? Any doubt in this topic? I close that, all present, I think so. Any doubt in this? God, basic, what is a semiconductor device? Yes or no? Are you clear now?
Yes, sir.
Has doubt? Yes, has a doubt?
No.
Okay.